We solve the 2024 MIT Integration B regular season set of questions. Question 1, question 2, question 3, question 4, question 5, question 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 questions that appeared in the regular season of MIT 2024 Integration B is going to be the subject of this video. We solve all these questions, and I hope you do enjoy sticking around with us. Thank you. So problem 1 is the integral from x equals to 1 to x equals 2024 of the floor function of the log to the base of 43 of x. Very interesting problem. The solution to the problem. I think the first thing that we'd like to do is to define what a floor function of the logarithm to the base 43 of x means. That means that when the log to the base 43 of x is between an integer k and k plus 1, that means that the floor function of the log to the base 43 of x is equals to the value or to the integer k. As soon as log to the base 43 of x is equals to k plus 1, then this floor function shifts to k plus 1. Now, what does it mean for x? That means that in that interval, k is greater or equal to 43 to the power k, integer k, and less than 43 to the power k plus 1. So when we now try to plot this within the interval provided, that is between x equals to 1 to x equals to 2024, we'll have the x-axis and the y-axis shown here. So we have x horizontal, and then we have floor function of the log to the base 43 of x on the vertical. So when k is 0, obviously this is 1, and therefore log, that means that between k is 0 and k equals to 1, the floor function is going to be k, which is 0. And then when k now increases, now from k, between k equals to 1 to k and k equals, and k plus 1, and that means 2, means that this is x is between 43 to the power 1 and 43 to the power 2, which is 1049. And then the next interval, and in this interval, therefore, the floor function is 1. And then for the next interval, 43 to the power 2 and 43 to the power 3, the floor function shifts to 2, right? So we said between 43 to the power 1 and 43 to the power 2, the floor function is 1. And between 43 to the power 2 to 43 to the power 3, then the floor function is 2. However, our interval of integration does not go to 43 to the power 3. It only stops at 2024. So our integration is going to be limited to this blue dotted rectangle. So what does that mean? That the integral of the floor function of 43 to the log the base 43 of x from x equals to 1 to 2024 is going to be equal to this area here, which is 43 to the power 1, which is 43 times 0 because the height is 0. And then this area here, which is 43 to the power 2 minus 43 to the power 1, which is 43, times 1, which is the height. And then this area here, which is 2024 minus 43 to the power 2 times 2, which is our height here. So you can pull out 43 out, and so we have 43, and then in the bracket we are still left with 43 minus 1, which is 42. So we have 43 times 42 times 1. And here 43 to the power 2 is the same as 1,849. So 2024 minus 1,849, obviously times 2. So this is 0, and here we have 1,806. And here we are left with 350, such that the final answer is 2,156. And this is the answer for this integral. Seemingly had a problem, but when you break it down to its core elements, it is easy to solve. So thank you so much for giving us your company. It was an absolute pleasure solving this problem. Until next time, adios. So problem number 2 is the indefinite integral of 1 over x to the power 2024 minus x to the power 4047. So now on to this problem. The problem really involves converting this problem or splitting it into partial fractions. And the first step would first of all be to factorize the denominator. And since x to the power 2024 is common to both of these terms, we can pull that out. And so now we have x to the power 2024 times 1 minus x to the power 2023. And then so we can proceed by now saying, okay, we want to express or divide this x to the power 2024 into 2 terms such that we have 2023 inside the bracket and also outside the bracket. So let's focus on creating a partial fraction out of 1 over x to the power 2023 times 1 minus x to the power 2023. So focusing on that, and we've emphasized that by changing the color to the blue. So what we're going to do is assume that x to the power 23 is u. So you have 1 over u times 1 minus u. That can be equivalent to 1 over u plus b over 1 minus u, right? We don't know the constants a and b, and we have to determine that. So if you multiply u times 1 minus u across, so we have 1 equals to a times 1 minus u plus b u. So collecting like terms, so we have a plus b minus a times u. Looking at the constants, A is equals to 1, obviously, and then B minus A is 0, right? Since we know that A is equals to 1, and from here we see B equals to A, then it means that B is also equal to 1. So therefore, 1 over U times 1 minus U is the same as 1 over U plus 1 over 1 minus U, and thus 1 over x to the power 2023 times 1 minus x to the power 2023 is the same as 1 over x to the power 2023 plus 1 over 1 minus x to the power 2023. So since we've figured out this partial fraction, we'll just go and plug it in. And so we have 1 over the integral of 1 over, our original integral is 1 over x to the power 2024 plus 1 over x times 1 minus x to the power 2023. So the issue now is, what does this really equal to? So we have to again engage in splitting this fraction into partial fractions. So I would like to emphasize that by, using a different color green. So 1 over x times 1 minus x to the power 2023 is the same as c over x, because we begin with the polynomial 1 degree lower than what we have in the denominator. And then 1 minus x to the power 2023, obviously the highest polynomial here is x to the power 2023. So in the numerator, we're going to have to generate a polynomial that runs up to a degree less than the highest degree in the denominator. And so we have done here, this is a summation from k equals to 0 to 2022. So we have d0, d1, d2, d3 up to 2022 with x to the power 1, x to the power 0, all the way to 2022, which is less than 2023. So to write that in a more explicit fashion, so we have c over x plus d plus d1x, d2x squared, up to d 2022 times x to the power 2022. So that's that. Now, if we multiply both sides by the denominator on the left-hand side, then what we're left with is 1 equals to c times 1 minus x to the power 2023. And then obviously, since we're multiplying x across here, we have d0x, d1x squared, all the way up to d 2022 x to the power 23. Collecting like terms, we have 1 equals to c plus d0x plus d1x squared, all the way up to d 2022 minus c, since we've gotten this here. So this is d 2022 minus c times x to the power 2023. As you can see, whatever is on the left-hand side, all these constants are 0, 0, 0, all the way up to here, and only c equals to 1. So c equals to 1, and then d 2022 minus c equals to 0, but that means that d 2022 minus is equals to c, and since c is equals to 1, we can also say d 2022 is equals to 1. So essentially, our fraction 1 over x times 1 minus x to the power 2023 is the same as 1 over x plus here d to the 2022 x to the power 2022 over 1 minus x to the power 2023. But since d to the 2022 is 1, so we have x to the power 2022 over 1 minus x to the power 2023. So this is our partial fraction. And so we're going to plug that into our integral, since we've already derived this. Our integral now is the integral of 1 over x to the power 2024 plus 1 over x, this one here, plus x to the power 2022 over 1 minus x to the power 2023. Okay, so just a little bit of clarity here. 1 is the same as the derivative of x in the denominator here, and then x to the power 2022 is the same as negative 1 over 2023 times the derivative of 1 minus x to the power 2023 here. So what this means is that this is the same as, when we integrate, this is the same as the natural log of x, and this is the same as negative 1 over 2023 times the natural log of 1 minus x to the power 23. So here, this is a very trivial integral. We have negative 1 over 2023, x to the power negative 2023 plus natural logarithm of x from integrating this minus 1 over 2023 times the natural logarithm of 1 minus x to the power 2023 plus the integration constant. And this is the answer that was provided. Thank you so much for those of us who have followed till the end. We do appreciate your support. We do appreciate you following us. We'd like to grow our channel. If you haven't subscribed to our channel, we do really encourage you to subscribe to our channel. Until next time, à tout à l'heure, la prochaine fois. So problem number 3 is the definite integral from x equals to 0 to x equals to 1 of x squared times into bracket 1 minus x to the power 2024. So this problem, I would use integration by parts. I like it because this is a very straightforward and easy to understand methodology. So what you do is, as I said, use integration by parts, where if you have a product of v du integrated, that would result into uv minus the integral of u dv. And so for this problem, if we consider v to be x squared and then du to be 1 minus x to the power 2024, then it means that u is negative 1 over 2025 times 1 minus x to the power 2025. So our integral v du, which is x squared times 1 minus x to the power 2024, integrated from x equals to 0 to 1 is it's uv, which is obviously this x squared times this u bounded between 0 and 1 plus, because this negative sign here interacts with this, we have a plus, the derivative of v, which is 2x, so 2 comes out, 2 over 2025, the integral from 0 to 1 of x times 1 minus x to the power 2025. Now, focusing on this uv part, this is the same as limit of x tending to 1 of this minus limit of x tending to 0 of this. Now, when x tends to 1, 1 minus 1 is 0, so this part goes to 0. So this part goes to 0. And then when x tends to 0, since this goes to 0, this entire part also goes to 0, right? So we're left with the integral of 2 over 2025 times x times 1 minus x to the power 2025, right? Then again, using integration by parts by setting v be equal to x, and then du being 1 minus x to the power 2025, that means that u in this stage is negative 1 over 2026 times 1 minus x to the power 2026. So now taking this integral all into account, it means that getting the constant where it is, our uv is x times this, which is negative x times 1 minus x to the power 2026 over 2026, obviously with the bounds 0 and 1, and then plus, again, this negative here interacting with the negative uv minus the integral, so this becomes positive. 1 over 2026, the derivative of v, which is x, is 1, so we just now have a bare integral of 1 minus x to the power 2026. So still, again, considering the limits, 1 and 0, as x tends to 1, as we can see, 1 minus 1 is 0, so this part tends to 0. And then as x tends to 0, this x here tends to 0, so this entire part also tends to 0. So we are left with the integral of 2 over 2025 times in bracket 1 over 2026, integral from 0 to 1 of 1 minus x to the power 2026. So if we integrate this, 1 minus x to the power 26. That's the same as negative 1 over 2027 times 1 minus x to the power 27. So with the limits taken appropriately, we can see that as x tends to 1, 1 minus 1 is 0, so this part tends to 0. This tends to 0. And then as x tends to 0, so this is 1 minus 0. So this tends to 1 over 2027, negative and negative, this becomes a positive. So we have 2 over 2025 times 1 over 2026 times 1 over 2027 as our answer. So this is how I would solve it, because I like taking it from the very foundational aspects of things, from the first principles. But most folks would look at this problem and then say, hey, why don't you use beta function and then gamma function? So that's what we're going to look at here. So we're going to use beta function for a second way of trying to attack this problem. And picking from Wikipedia, the beta function of z1 and z2 is the integral from t equals to 0, t equals to 1 of t to the power z1 minus 1 times 1 minus t to the power z2 minus 1. And so expressing our problem into this format here, that means that our z1 is 3, because 2 is 3 minus 1, and 2024 is 2025 minus 1. So this problem here can be expressed as a beta function of 3 and to the 25. Now, if we express this beta function in terms of gamma functions, because that's what would really help us to solve it, from Wikipedia again, if you have a beta function of z1 and z2, that's the same as the gamma function z1 times gamma function of z2 all over gamma function of z1 plus z2. So therefore, if our beta function is of 3 and 2025, then that's the same as the gamma function of 3 times gamma function of 2025 over gamma function of 3 plus 2025, which is the same as the gamma function of 3 times gamma function of 2025 over gamma function of 2028. Now, from definition, a gamma function of an integer n is the same as n minus 1 factorial. And so this problem here now becomes 2 factorial, 3 minus 1 factorial is 2 factorial. 2025 gamma function is the same as 2024 factorial over 2028 gamma function is the same as 2027 factorial. So 2024 factorial is 2024 times 2003 all the way up to 1. 2027 is the same as 2027 times 2026 all the way to 1. So you see that 2024 factorial cuts this denominator at 2024 factorial. So in other words, the denominator just becomes 2027 times 2026 times 2025. And then 2 factorial is the same as 2. So this is your answer, 2 over 2027 times 2026 times 2025. And this is our answer. Thank you so much for hanging out with us. It's been an absolute pleasure solving this problem with you. If you have any question, please don't hesitate to leave a comment in the comment section. I would look forward to interacting with you. We love mathematics. Mathematics is our passion, and we'd like to share that passion with you. Thank you. Until next time, adios. So problem number 4 is the indefinite integral of 2023 x plus 1 over x squared plus 2024. As you can see, I personally would be inclined to separate it into 2 different fractions. So we would split it into 2023 x over x squared plus 2024 plus 1 over x squared plus 2024. So if we create this as 2 separate integrals, we have the blue integral and the green integral, the blue being 2023 x over x squared plus 2024, and the green one being 1 over x squared plus 2024. So we would solve this integral separately. I would personally be inclined to bring out the constant 2023, and then x can be expressed as half the derivative of x squared plus 2024, which is the denominator. So as we know, with the integration, if you have a fraction, polynomial that's a fraction, and the numerator is the derivative of the denominator, and then the integral of that function would be the natural logarithm of the function in the denominator. So essentially, we can pull half out, and so we have 2023 over 2 times the natural logarithm of x squared plus 24 as the integral of the blue integral. Now, we can now move forward to try and focus on the green integral. And the best thing to do here, I think, is substitution. There is a direct way, if you're very used to integrating such functions, it will be intuitive enough to know what the integral of this is, but we're going to try and do it from the very basics. So we could say let x be equal to the square root of sin 24 tan theta, such that the x d theta is square root of sin 24 sec squared theta. And so therefore we can substitute dx with square root of 2024 sec squared theta d theta. So this dx here. Now this integral now becomes one of the integral 1 over x squared plus sin 24 could be equal to 1 over, in place of x, we have the square of this, which is 2024 tan squared theta plus sin 24. And then in place of dx, we have the square root of 2024 sec squared theta d theta. So the denominator, we can factor 2024 out, and so we have 2024 plus tan squared theta plus 1 in the denominator. And so pulling the tan squared theta plus 1 is the same as sec squared theta. And then we can pull the constants out. So we have the square root of 2024 over 2024, integral of sec squared theta over sec squared theta. And so the sec squared theta obviously would cancel with one another. And so the division of square root of 2024 by 2024 is the same as 1 over square root of 2024. And the integral times the integral of 1. So this becomes 1 over square root of 2024 theta plus the integration constant. Now, since we said x is equal to square root of 2024 tan theta, that means that theta is equal to, when you divide both sides by square root of 2024, so we have x over 2024 equals tan theta, and therefore theta is the arctangent of x over square root of 2024. So what that means essentially is that this integral being this is the same as the integral of 1 over x squared plus 24, the same as 1 over square root of 24 plus of theta, we have arctangent of x over 2020 square root of 2024. So this now can be substituted back to the original integral of 2023 plus 1 over x squared plus 2024, being equal to 2023 over 2 natural logarithm of x squared plus 2024 plus this green integral. And in place of this green integral, we now have 1 over square root of 2024 arctangent x over square root of 2024. And then obviously we add the integration constant. So this is our final answer. It's not uber complicated, easy, but also not very easy, but I believe it's also an interesting problem. So if you do have any questions in regard to some of the steps we chose to follow, please leave a comment or a question in the comment section. We'll definitely get back to you. But it was really an absolute pleasure to share our version of the solution with you. Until next time, à la prochaine fois. So problem number 5 is the definite integral from x equals to 0 to x equals to pi over 2 of sec squared x times e to the power negative sec squared x. This problem is interesting. The first thing I'll definitely do is, as I said, this one here means our x is in the power here. It's just weird. So first thing is we would like to use this identity where tan squared x plus 1 is equal to sec squared x. So what that means is that for a problem, what we'll do is, as we say, this x is in the power. We'll replace sec squared x with tan squared x plus 1. And what that means is that using the rules of exponents, we can pull out e to the power negative 1, and then we're left with sec squared x times e to the power negative tan squared x. Now, if we say let u be equal to tan x, what that means is that du dx is sec squared x. And so we can substitute for sec squared x dx with du, right? And then for the limits, when x equals to 0, tangent of 0 is 0, so u is 0. As x approaches pi over 2, u would approach infinity. So now, since our original integral is equal to, again, this x goes to the power here instead of it being in the base, is equals to e to the power negative 1 times the integral from x equals to 0 to x equals to pi over 2 sec squared x times e to the power negative tan squared x. So obviously, e to the power negative 1 is 1 over e. And now we see that sec squared x dx can be replaced with du. This goes to pi, infinity, pi over 10 goes to infinity, and this is 0. And this here goes to negative u squared, right? So applying all those transformations or changes, so we're left with this very nice tractable half integral, half Gaussian integral. And so if we are to, since the Gaussian distribution is symmetrical about x or u equals to 0, if we are to consider that, then we have to add a constant over half. So 1 over 2e times the integral from u equals to, or u tending to negative infinity to u tending to positive infinity of e to the power negative u squared du. I mean, e to the power negative u squared. So this is a Gaussian integral, and it does have a popular answer to it, which is square root of pi. And so our answer now is 1 over 2e times the square root of pi. And this is the answer that was expected. Very interesting. But it did require quite a bit of transformation, substituting for the trigonometrical functions with u. And that led us to this answer. So if you haven't subscribed to our channel, we do really encourage you to consider subscribing to our channel. We thank you so much for your continued support. For those of you who have subscribed to our channel. Until next time, bye-bye. Telugu love question for. Thank you. So problem number 6 is the indefinite integral of cot x times cot of 2x. This problem is interesting. First thing that a person would do is I could express the cotangent functions, cotangent x and cotangent 2x in form of sine x cosine x sine 2x, cosine 2x respectively. So as we can see, this function is the same as the integral or the integral of cotangent x cotangent 2x is the same as the integral of cosine x over sine x times cosine 2x over sine 2x, sorry. And so keeping the single angle formalism as they are, we could now go ahead and express 2x as 2 sine x cosine x. So what that results into is this cosine x would cancel with that. So we have in the numerator 1 times cosine 2x. In the denominator we have sine x times sine 2 sine x. So cosine 2x can be also expressed as cosine squared x minus sine squared x. And then the denominator, we have 2 sine squared x. So we can pull the half out so that we have the integral of cosine squared x by sine x is cotangent squared x. And then sine squared x by sine squared x is 1. So this is interesting. We could also now go ahead and say if we have the identity cotangent squared x plus 1 equals to cosecant squared x, that means that our integral now could be transformed by substituting cotangent squared x being equal to cosecant squared x minus 1. So if we plug this into our integral, now we have half the integral of cosec squared x minus 1 minus 1. And so that means that we have half the integral of cosec squared x minus 2, and multiplying half across, so we have integral of a half cosec squared x minus 1. So this means that the integral of cosec squared x is the same as negative cotangent of x, and we'll prove why that is the case later. And then the integral of negative 1 is negative x plus integration constant c. So this is the answer. There's another way of looking at this problem is by expressing cotangent x and cotangent 2x in form of tangent x and tangent 2x respectively. So of course cotangent x times cotangent 2x is the same as 1 over tan x times 1 over tan 2x. Then we know that tan 2x is the same as twice tan x over 1 minus tan squared x. So substituting these in place of these, we get that cotangent x, cotangent 2x is the same as 1 over tan x here times 1 over 2 tan x divided by 1 minus tan squared x. So the reciprocal of this becomes now 1 over tan x times 1 minus tan squared x over 2 tan x. And so multiplying tan x and 2 tan x becomes 2 tan squared x. So we have now, by pulling this half out here, we have half 1 minus tan squared x over tan squared x. Then 1 minus tan squared, 1 divided by tan squared x is the same as cotangent squared x. Tan x divided by tan squared x divided by tan squared x is 1. So we go back to the same expression of half cotangent squared x minus 1, which reduces to a half cosec squared x minus 1, which is cosecant squared x minus 2, which is a half cosec squared x minus 1. And then when we integrate that, we get the integral of half cosec squared x minus 1, which we found out to be negative half cotangent x minus x plus c. So this is obvious, very obvious, based on the first solution that we're able to derive. But we would also like to show why the derivative of cotangent x is the same as negative cosec squared x. So if you differentiate cotangent x is the same as the derivative of cosine x over sine x, which is using the product rule, 1 over sine x times the derivative of cosine x plus cosine x times the derivative of 1 over sine x. Now, if you know that the derivative of capital U over V, capital V is equals to V, the derivative of capital U minus capital U the derivative of capital V over V squared, the quotient rule of differentiation. That means that when we focus on the derivative of 1 over sine x, V is sine x, U is 1. So what that means is for the first part is 1 over sine x, the derivative of cosine x negative sine x. Cosine x, now the derivative of 1 over sine x, the denominator, V squared is sine squared x. V being equal to sine, and then the derivative of 1 is 0, minus U being 1, derivative of sine x is cosine x. So we have 0 minus cosine x. And so this and this cancels, but we have negative 1 here, minus cosine times cosine, this cosine squared x over sine x. So which is negative sine squared x plus cosine squared x over sine squared x. This identity is equals to 1. So we have negative 1 over sine squared x, which is negative cosecant squared x. So, and this here brings us to why we're able to obtain cotangent x when we negative cotangent x when we integrated cosecant squared x. So that's the quick of it. Thank you so much for following along. If you have any question, please leave your comment or question in the comment section. We'll definitely get back to you, but it's been an absolute pleasure running through this problem. Until next time, be safe. Bye-bye. So problem number 7 is the indefinite integral of hyperbolic sine squared x over the hyperbolic tangent of 2x. The problem, as I said, is interesting. The first thing that we would like to do is first of all express the hyperbolic tangent of 2x in form of the primary hyperbolic sine and cosine terms. So here we have hyperbolic tangent of 2x being equal to hyperbolic sine of 2x over hyperbolic cosine or cos 2x. So this now becomes hyperbolic sine squared of x times hyperbolic cosine 2x over hyperbolic sine of 2x. Now, a few identities that we can use: hyperbolic cosine of 2x the same as hyperbolic cosine squared of x plus hyperbolic sine squared of x. And then hyperbolic sine 2x the same as 2 hyperbolic sine x cosine hyperbolic sine x, hyperbolic cosine x. And therefore, also, one other identity that's interesting is hyperbolic sine squared x minus, made a mistake here. So hyperbolic cosine squared x minus hyperbolic sine squared x is equals to 1, which means that this one here, this first identity, we're substituting for sine hyperbolic sine squared x with 1 plus hyperbolic cosine x. We get that hyperbolic cosine 2x being equal to 2 hyperbolic cosine squared x minus 1. So if we take this expression here and substitute for whatever is in the numerator, and then the denominator is so here substituting for what is the numerator here, and the denominator hyperbolic sine 2x the same as 2 hyperbolic sine x hyperbolic cosine x. And as you can see, this cancels with 1 of the hyperbolic sine of x there, And so we do have now hyperbolic sine x times 2 hyperbolic cosine squared x minus 1 over twice hyperbolic cosine x. Now we can pull the half out, and we have now this multiplied by this divided by this. Since this cancels with 1 for this term, we have 2 hyperbolic sine x times hyperbolic cosine x minus hyperbolic sine x over hyperbolic cosine x. And this here is the same as hyperbolic sine 2x. And on the second term, hyperbolic sine x is the same as, it's the derivative of hyperbolic sine, cosine x. And any expression like this, when integrated, is the same as the natural logarithm of the function in the denominator. So going ahead, this becomes half when integrating hyperbolic sine 2x, that becomes half hyperbolic cosine 2x minus the natural logarithm of hyperbolic cosine x. So this is a quarter hyperbolic cosine 2x minus a half log hyperbolic cosine x plus c. And this is our answer that was provided in the question. So thank you so much for tuning in. If you have any question, please feel free to leave a question or a comment in the comment section. We'll be glad to get back to you. It was an absolute pleasure solving this problem. Until next time, bye-bye.
So problem number 8 is the indefinite integral of the arctangent of the square root of x.
One thing I would do is to let u be equal to that square root of x, and this is just a personal proclivity that I substitute for what seems to be a complicated expression with simpler ones. So when that is the case, then u squared is equals to x, and so 2u du dx is equals to 1, and therefore we can substitute dx with 2u du. Yeah, so that comes from obviously multiplying with dx on both sides, left and right. And so now arctangent of square root of x integrated is the same as arctangent. In place of square root of x, we have u. In place of dx, we have 2u du. And so we can pull out the constant u, and so we have the integral of u, arctangent of u. And now we can also express u as a derivative of u squared times a half, and then times arctangent of u. Now we can use now integration by parts, where if you have the integral of the product of u and dv, the result is uv minus the integral of vu du, right? And therefore, if now we set u to be arctangent of u, and then therefore du, capital U, or is the same as this the derivative of arctangent of u, which is 1 over u squared. And if dv is the derivative of u squared, then it means that v is u squared. And so since this 2.5 here cancel, therefore the derivative of u squared times arctangent of u is the same as uv, which is u, which is arctangent of u, and v, which is u squared, so u squared times arctangent of u, minus v du, so v here is u squared, du is 1 over u squared. And now we can do long division here, just to make things easy. So if you have u squared here, and you have 1 plus u squared outside here, multiply by 1, so we have u squared plus 1 here, and so we have a difference, a residue of -1. So this fraction here is the same as 1 minus 1 over 1 plus u squared. Yeah, and this coming from here, and this -1 here coming from this portion here. And so now we can plug that in here. So we have u squared, arctangent of u, minus 1 over u squared. Okay, so integrating 1 minus 1 over u squared, the integral of 1 is going to be u, and then the integral of 1 over 1 plus u squared is the non-arctangent of u. Okay, we won't go into details on how to integrate this. It's a very obvious thing. And then so collecting like terms, u squared and 1 here, so u squared plus 1 times arctangent of u minus u plus c. But since we had initiated our substitution with u being equal to square root of x, then wherever u appears, we have square root of x, therefore meaning that u squared is x, and so the arctangent of square root of x integrated is the same as plus of u squared x plus 1 arctangent u being equal to square root of x minus here u, we have square root of x plus c. And this is our answer here. Very interesting problem. I hope you did enjoy following along. If you have any questions, please feel free to leave a question or comment in the comment section. We'll be glad to get back to you. Until next time, bye-bye.
So problem number 9 is the definite integral from x equals to 0 to x tending to infinity of x times natural logarithm of x over x to the power 4 plus 1.
So this is an interesting problem. The first thing that I would do is, as I said, I look for a more complicated expression and I use u to substitute that instead. So if u equals to natural logarithm of x, then du dx is equals to 1 over x. And what that means is that x du can be substituted for dx. And what is x if u equals to log x? It means that e to the power u is equals to x. So in other words, the expression e to the power u du can be substituted for dx. Now, in terms of the limit when x equals to 0, u tends to negative infinity, because when x approaches to 0, this log of x approaches infinity. So lower limit, x tends to u tends to infinity. Upper limit remains u tending to infinity. So the integration from x equals to 0 to x tending to infinity of x log x over x to the power 4 plus 1 is the same as in place of x in the power u in place of log x u in place of x to the power 4 is e to the power u to the power 4, which is e to the power 4u plus 1. And in place of dx, we have this e to the power u du. And we can consolidate these two, e to the power u times the power u, which is e to the power 2u times u over e to the power 4u plus 1. Now, the limit, as I said, negative infinity to positive infinity. But now we can separate this integral into two parts, where we integrate from x, from u to the tending to negative infinity to u equals to 0, and then from u equals to 0 to u tending to infinity, right? And therefore, what now that means is that these two separate integrals can be played around with separately. Let's focus on the upper integral. If we divide both the numerator and denominator by e to the power 4u, and this is what we're showing here, you divide the entire denominator by e to the power 4u, the entire numerator by e to the power 4u. What that means is that in the numerator, we are left with e to the power negative 2u times u over 1 plus e to the power negative 4u, because e to the power 4u in the denominator divided by e to the power 4u becomes 1, and then this 1 divided by e to the power 4u becomes e to the power negative 4u. And then now let's go and focus on this side of things. If we say let u be equal to negative u, I know what this means is that du, let's use prime here, is equals to negative du. And then this negative infinity becomes positive infinity, but here we have e to the power negative 2u. This becomes negative u prime, and then it's negative, and the negative here becomes positive, so the sign does not change. So essentially we have e integration from u turning positive infinity to 0 of this becomes negative e to the power negative 4u plus 1 e to the power negative 2u u du. So the negative from this u and the negative from the du cancel out, so we have a positive. Now when we flip the signs so that this interval, not the signs, but if we when we flip the limits, then we have to attach a negative to this side. So now we do have this integral, which is the same as this integral, but opposite in sign. So what that means is this and this would cancel out, right? And that means that the answer is 0, right? So that's the answer for this very interesting problem. Looked complicated, but when you play around and manipulate things, you're able to arrive at the answer very easily. So thank you again for paying attention, for following along. If you have any question, please don't hesitate to leave a comment or a question in the comment section. We would be glad to get back to you. So until next time, bye-bye.
So problem 10 is the definite integral from x equals to 0 to x equals to 10 of the floor function of x times the floor function of x. So we have nested floor functions here.
Interesting. The first thing that obviously we would like to just remind ourselves is what a floor function is. So if we have a variable x that is less than k plus 1, but also greater or equal than k, then it means that the floor function of x is k for the entire duration. And as soon as it falls, x falls between in the interval where it is greater or equal to k plus 1 and less than k plus 2, then the floor function of x now becomes k plus 1. So that means that now our integral of the floor function of x times the floor function of x from 0 to 10 is between 0 and 1, since the floor function of x there is 0, so it's 0 times x floor function. Between 1 and 2, since the floor function of x there is 1, so we have the floor function of x. And then between 2 and 3, since the floor function of x there is 2, so we have 2x floor function. And we keep adding until we get to the interval 9 to 10. The floor function of x within that interval is 9, so we have the floor function of 9x integrated in that interval. So since this is 0, so that collapses to 0, and now we have a summation of integrals from 1 to 2, floor function of x, 2 to 3, floor function of 2x, and so on up to the interval 9 to 10, where we have the floor function of 9x. So that can easily be represented as a summation from k equals to 1 to 9 of the integral from k to k plus 1 of the floor function of kx. So let's try to see what this integral looks like. So yeah, we do have interval k to k plus 1. And so at k, we have the value being k times k, which is k squared, right? And that continues all the way until when x equals to k and 1 over k, then that now shifts to k squared plus 1, right? Because k times k and 1 over k is k squared plus 1, right? And then so it continues in that at that value up to when k is, x equals to k and 2 over k. And at that point, it transitions to k squared plus 2 and so on until now we come to k and 9 over k and k minus 1 over k. At that point, we have k squared plus k minus 1. And that continues until when x equals to k plus 1. And then it transitions to k squared plus k. But this is what happens. And so the integral now means that since the spacing here is 1 over k, 1 over k, 1 over k, so we have k squared times 1 over k. And here we have k squared plus 1 times 1 over k. Let me just represent this nicely. So we have this rectangle here, which has the height k squared and the width 1 over k. And then we have this other rectangle, we have the height k squared plus 1, but the width still remains 1 over k, and then so on, right? And then, keep doing that. So that until we have this last rectangle where we have k squared plus k minus 1 times 1 over k. So this is how you're going to represent it. And so essentially what happens here is that now we do have a summation or from k equals to 1 to 9. And in there we have now different strips within the interval of k. We have now the width 1 over k times k squared plus L. So where L now straddles between 0 and k minus 1. So, when L is equals to 0, we have k squared times 1 over k. When L is equals to 1, it's k squared plus 1. And L is equals to 2, k squared plus 2, and so on until we come to k minus 1. So this summation here, when L is equals to 0, we have 1 over k times k squared, and then plus the summation from L equals to 1 to k minus 1, right? And that means that we're keeping this 1 over k times k squared plus 1 over k. This k in this summation is a constant, so we just now have k squared times k times 1 plus this L here using your arithmetic progression is, so the summation of L from L is equals to 1 to n is the same as n over 2 times n plus 1, right? And so n here is k minus 1, which is here. N plus 1 is k all over 2. That's what we've done here, right? And so we continue by saying now this is 1 over k because we pulled out 1 over k, this 1 over k and this 1 over k out. We have now k squared plus k squared times k is k cubed minus k squared times this negative 1 is minus k squared plus k squared minus k over 2. 1 over k, so we multiply 2 across, and then we have it all divided by 2. So we have this cancel with that. And so we have 2k cubed plus k squared minus k. And this, we can pull this half out so that we have 1 over 2 out, summation of this k divided by this k cube, it results into k squared. This goes away, and then this goes away, and we are left with 1 here. So we have 2k squared plus k minus 1. So we now have our integral being equal to a half times the summation from k equals to 1 to 9 of 2k squared plus k minus 1. And now just the popular things that you could know from part. Summation from k equals to 1 to n of k squared is the same as n times n plus 1 times 2n plus 1 over 6. The summation of k from k equals to 1 to n is n times n plus 1 over 2. So we can plug this in here with n being equal to 9. And so for this k squared, we have 2. And in place of n, we have 9. In place of n plus 1 is 10. In place of 2n plus 1 is 2 times 9 plus 1, which is obviously 19. And then for this k, we have n is 9, n plus 1 is 10, all divided by 2. So this 2 divided by 6 is 3, and then the 3 and 9 we have 3. So, and then this 2, and we have 5 here, right? So we have a half, 3 times 10 times 19, plus 9 times 5 minus 9. And here, this is the same as pull 9 out, 5 minus 1, yeah, from this set of, which is 9 times 4, right? Ooh. So we have a half, 3 times 10 times 19 plus 9 times 4. And now this is 30 times 19, which is 570, 9 times 4 is 36, which is a half times 606, which is equals to 303. And this is the final answer for this problem. Certainly a very interesting integral, but I hope you're able to follow along. If you have any questions, please feel free to leave us a question or a comment. We'll be very glad to get back to you. Certainly would like to interact with you and, just start a conversation. I would love to learn from you as well. If you have any suggestions, we're very much open to hearing from you. Well, until next time, it was an absolute pleasure solving this problem and giving you a version of what we think is an answer or a method that could lead to an answer that is interesting. Other than that, until next time, bye-bye. See you.
So problem 11 is the definite integral from x equals to 0 to x equals to 1 of e to the power negative x times the square root of 1 plus the cotangent square into bracket of a cosine of e to the power negative x.
So with this problem, first thing I would do is substitute for e to the power negative x, and just letting u be equal to e to the power negative x means that du dx is equal to negative e to the power negative x, such that du equals to negative e to the power negative x dx. So we can substitute for the product of, indicate this, for the product of e to the power negative x and dx with the du negative. Also, the limits when x equals to 0, u is equal to e to the power 0. When x equals to 1, we have e to the power negative 1. So essentially, our integral here now, trying to reorganize a little bit, bunching this e to the power negative x and this dx together, and then trying to differentiate it a little bit by having a different color. So this part here can now be substituted with du negative, right? And then this can be substituted with 1, that is e to the power 0, and this with e to the power negative 1, and then this with u, right? So doing that means that now we do have a much tractable integral. We can now remove this sign here coming from this by flipping the limits. So the upper limit goes lower, and then the upper limit, the lower limit goes up. And so now we do have the integral from u equals to e to the power -1 to u equals to 1 of the square root of 1 plus the cotangent squared of cosine of u. Now we can express this cotangent as the fraction of cosine squared arc cosine u over sine squared arc cosine u. And then making this sine squared as a common denominator inside the square root sign means that now in the numerator we have sine squared plus cosine squared, which is an identity that leads to that numerator being equal to 1. And then the denominator remains as sine squared arc cosine of u. Using the same identity, we can now express the sine squared component as 1 minus cosine squared arc cosine of u. And that means that we have now the integral of the square root of 1 over, because this here is the same as u squared, right? So cosine arc cosine u times cosine arc cosine of u, which is just u squared. And so the square root of 1 up there, we have 1 over square root of 1 minus u squared. So 1 comes out of the square of sine that way. We can now do another substitution by letting u be equal to sine theta. That means that du d theta is cosine theta, and therefore we can substitute for du with cosine theta d theta. Now the limits when u equals to e to the power -1, e to the power -1, theta becomes arc cosine e to the power -1, and when u equals to 1, arc cosine of 1 is pi over 2. So we have substituted appropriately. Where we have u, we have sine theta. Where we have these limits, we have appropriately substituted the limits that we've found here, and then with du being equal to cosine theta d theta, that has been substituted appropriately. So the square root of 1 minus sine squared theta is the same as square root of cosine theta, which is the same as cosine theta. So this cosine theta is cancelled, and so we are left with the integral from theta equals to arc cosine with the power -1 to theta being equal to pi over 2 of 1. And that results into, obviously, theta with the limits shown here. And so we have pi over 2 substituting plus of theta minus the lower limit arc cosine e to the power -1. And this is the answer. Very interesting. Thank you so much for following along. We appreciate your support. Until next time.
So problem 12 is the definite integral from x equals to 1 to x equals to 3 of 1 plus and a recursive function of obviously 1 plus dot 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 over x plus dot dot dot, all that over x plus 1 over 1 plus dot 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 over x plus dot dot dot. So this is a recursive function where the entire function is repeated in each addition that you see both in numerator and denominator.
On to the solution of this problem, we could extract the integrand and say let u be equal to the integrand. And as you can see, this top part here is the same as u, right? And also that bottom part seems to be also equal to u. So essentially, you do have an expression like this, u being equal to 1 plus u over x plus u. And then if you multiply across both sides with x plus u, we get that ux plus u squared is equals to 1 plus u. Now what we've really done here is we've multiplied times 1 plus, x plus u here, and then this side as well, x plus u, right? That's what we've done. And so when you multiply by u, this is xu, u squared equals to this and that would cancel, and you have 1 plus u. Now you rearrange by pulling everything on the right to the left. We eventually have an expression, a quadratic expression, u squared plus x minus 1 times u minus 1 equals to 0. Now this is good. We are heading somewhere. What we do really need to extract is u in terms of x. So we have this quadratic expression, and we use the quadratic formula x squared plus bx plus c equals to 0. We know that the formula that gives us x is x equals to minus b plus minus square root of b squared minus 4ac over 2a. Now for u, the b is x minus 1 and the c is negative 1, right? Such that u, using the quadratic formula, is negative, b is negative, therefore x minus 1 plus minus b squared is x minus 1 squared minus 4ac, that means it's 4 times positive 1, which is a, and then times negative 1, which is c, and therefore we get plus 4 here. All over 2 times 1, since a is 1 here, and so we have over 2. So this is interesting, very, very interesting. We are not going to use both answers. We have minus x minus 1 plus square root of x minus 1 squared plus 4 over 2, and minus x minus 1 minus square root of x minus 1 squared plus 4 over 2. So there has to be some level of discernment here. We need to know which answer really is correct and equals to u in the interval 1 to 3. So in the interval where x is between 1 and 3, we know that since x is positive for all this domain, u must be greater than 0. And looking at this answer, there's only one option that is greater than 0, and that is negative x minus 1 plus square root of x minus 1 squared plus 4. Because at x equals to 1, x minus 1, this is 0, 0 squared plus 4 is 4, 4 square root is 2, and this x minus 1 here is 0. So we have essentially 2 over 2, so we have 1, and that increases. That decreases, but at least this answer here is greater than 0 in this interval here. So we choose this because the negative one, the minus x minus 1 minus square root of x minus 1 squared plus 4 over 2, that is negative already at the point 1. So we're choosing this, and we're going to use this to do the integration. And we've decided to plot these two values using Desmos. And as you can see, the negative one, this one here, is also negative in the interval between 1 and 3. And only this blue, where there is a plus in between here, is what we need. This is the one that we're going to use. So we quickly go in and plug in place of these complicated nested fractions. We just plug in the integral from x equals to 1 to x equals to 3 of negative x minus 1 plus the square root of x minus 1 squared plus 4 over 2. And so you can pull out a half. And since I don't really like playing with this x minus 1 business here, I can substitute for x minus 1 with y. And so dy dx is 1, and so dy is dx. And then for limits, when x equals to 1, y is 0, and x equals to 3, y is 2. And so we just come back and plug everything in there. So we have the integral of a half negative y, and then the plus the integral plus a half times integral from y is equal to 0 to 2 of square root of u squared plus 4. This first integral is easy because that is the same as we can first of all just differentiate these two integrals using the color coding. So we have the first one as blue and then the second one as green. And then when we integrate negative y, it's the same as negative y squared over 2. And then we have this constant half here with the limits as applied appropriately. So we have 2 squared over 2 minus 0 squared over 2 negative negative. And that means we have half negative 4 over 2. And that's the same as negative 4 over 4. So that means it's negative 1 for the first integral. Now the second integral is what really becomes a little bit complicated. So we're going to pull it out. We can use a trigonometrical substitution. If we, in place of y, we put like 2 tan squared theta plus 4. So 2 tan theta all squared. So we have 4 tan squared theta. So we can factor out 4. We have tan squared plus 1, and that becomes sec square theta, and then square dot sec theta. So that is one option we could do. So let y be equal to tan theta, 2 tan theta, therefore dy d theta is 2 sec squared theta. And so we can substitute for dy with 2 sec squared theta d theta, right? And then with the limit, when y equals to 0, 0 equals 2 tan theta, 0 divided by 2 is 0, arctangent of 0 is 0. The same with y equals to 2, 2 divided by 2 is 1, arctangent of 1 is pi over 4, so theta is pi over 4 at this upper limit. So we have 0 to 2 square integral of y squared plus 4. That is same as from theta equals to 0 to pi over 4 of square root integral of 4 tan square theta plus 4 times, in place of dy we have 2 sec square theta d theta, right? And so pulling out the 4 square root, that becomes 2. And so in bracket, in the square under square root sign, we have tan square theta plus 1. And then we have 2 sec square theta d theta as a substitution for dy. And then now we can now multiply this 2 and this 2 to make it 4. And we know tan square theta plus 1 is sec square theta. Square root is sec theta. So we have left with the integral of sec theta times sec squared theta. Let's consider this to be I, so that the integral is for I here, right? So then we can go ahead and express sec squared theta derivative of tan as a derivative of tan theta, right? Then using integration by parts, where if we have u, product of u capital U and product of d capital V, when you integrate that, you have uv minus the integral of capital V times d, the integral of u, right? And so v here is tan theta, sec theta is u, so that uv here will be sec theta, tan theta, minus the integral of derivative of sec theta is obviously sec theta tan theta, and times tan theta, we have sec theta tan square theta. So obviously, as we said, uv is this with the limits applied appropriately, and then the product of v du, we have sec theta tan theta times tan theta. And then we have 4 as a constant here. So this here, multiplying these 2 is the same as tan squared theta, obviously. And then tan squared theta is the same as sec squared theta minus 1. And so when you plug that in, we can now get some things simplified a little bit. So we have the integral of here, sec cube theta. And since we had 4i here, so this specific part becomes And that's why I used 4i previously so that we can extract this out. And so keeping everything as it is and then separating this as two different integrals. And we're saying that this is I, right? And this negative and negative, this becomes positive. We can now pull this I onto this other side. So we have 4i and multiplying this 4 times this I, we have 4i. So pushing it to the left-hand side, we have 8i. And to revert back to the 4i, we have to divide both sides by 2. So you realize that this 4 now becomes 2. And then we have that integral reducing to this. And then you can now start substituting in the limits. So sec pi over 4 tan pi over 4 minus sec 0 times 0. So sec pi over 4 is the same as 1 over cosine pi over 4. And we know pi over 4 of cosine of pi over 4 is the same as cosine of 45 degrees, which is 1 over square root of 2. Yeah. And so this is same as square root of 2. And we already know that tan of pi over 4 is 1. So essentially we have 2 here, root 2, and then plus the integral. Because this goes to 0, this goes to 1, and this goes to 0. Right? So this entire thing goes to 0. And so we're left with a very interesting integral, which is the integral of sec theta. And here we're going to have to play some acrobatics, right? So sec theta is the same as 1 over cosine theta, right? And then what we can do is we can multiply the denominator and the numerator with 1 plus sine theta, right? Because when you really look at this, you can cancel this and still be left with 1. And then when you multiply this across, we have 1 plus sine theta over the product of 1 plus sine theta, cosine theta. Now 1 is the same as cosine squared theta plus sine squared theta. So when we plug that in, right, we do have cosine theta plus sine squared theta plus sine theta over 1 plus sine theta times cosine theta. Now we can factorize this part here by pulling sine theta out. And so we have here cosine squared theta plus sine theta times in bracket 1 plus sine theta. Now we can separate this as two separate fractions. So we have cosine theta over 1 plus sine theta, because this cosine squared divided by cosine, the 1 cosine goes away. And here, as you can see, sine theta times 1 plus sine theta divided by this. So this and that will cancel. So we have sine theta plus cosine theta. Now this is very easy to integrate, right? And so this is the same as 2. We have this constant here. Since the numerator is the same as the derivative of the denominator, so we have the natural logarithm of 1 plus sine theta here. And then here, this is negative, the derivative of the denominator. Here we have negative natural logarithm of cosine theta. You can bunch these together by dividing this and combining it into one log function. So we have 2 root 2 plus 2 log 1 divided by cosine theta is sec theta, sine theta divided by cosine theta is tan theta. And we have the limits applied appropriately. So we have 2 root 2 plus 2, applying in the limits, natural logarithm second of pi over 4 plus tan pi over 4 minus log of sec 0, sorry, here, plus tan theta, tan 0, sorry. And so all this goes to 1, right? This goes to 1, and this goes to 0. So log of 1 is 0, so that goes to 0. This goes to 0. Okay. And then sec of pi over 4, we found it to be root 2. Tan of pi over 4 is 1. So we have 2 natural logarithm of 2 square root of 2 plus 1. And that is the value we get from integrating the square root of y squared plus 4 from 0 to 20. Right? However, we saw that our original integral is -1 plus a half. The integral from 0, y is equals to 0 to y equals to 2 is the square root of y squared plus 4. And we've already now determined that this part here is the same as root 2 times root 2 plus 2 times natural logarithm square root of 2 plus 1. And so this is that, and that goes, and goes. And so we're left with -1 plus root 2 plus natural logarithm of 2, natural logarithm square root of 2 plus 1. Rearranging it in a way that, because root 2 is greater than 1, so we have square root of 2 minus 1 plus the natural logarithm 2 plus 1. And this is the answer that was provided. It was a little bit windy. Now there's a second method that probably is a more tractable way of looking at it. I personally don't like using hyperbolic sine and cosine for these kind of things, but that could have been a shorter option. So it's all about being open-minded, being open-minded about these things. So if we take the option where we say y equals to 2 hyperbolic sine of x or sinh x, therefore dy dx is 2 cos x. That means that you can substitute for dy with 2 cos x dx, right? And then now if you have the limit 0 and 2 for y, when y is equals to 0, that means that 0 equals to 2 sinh x, and divided by 2 means that sinh x is equals to 0. Point. So, right, and that means that e to the power x plus minus e to the power negative x over 2 is that is equals to 0. That means that e x minus e negative x equals to 0, and which is e to the power 2x 1 equals to 0. So e to the power 2x equals to 0, 1, sorry. Natural logarithm 2x is equals to natural logarithm of 1, which is 0, and so x is 0. So that's y. We have 0 in place of y for x, right? And then obviously when when y equals to 2, what we're doing here is we get 2 here, and 2 divided by 2 means that we have sinh or hyperbolic sine of x equals to 1, and therefore x is equals to the arc hyperbolic sine of 1, and that's what we're left with. So the limits, we devise them appropriately. So we have 0 in place of the lower limit, upper limit, arc sinh or arc hyperbolic sine of 1, and then in place of y we have 2 hyperbolic sine of x, so that squared is 4 hyperbolic sine squared x plus 4 times 2 cos x dx. And so this, we can pull out the 2 out, square root is 2, and hyperbolic sine is squared plus 1 is the same as cos squared, square root we have cos x. And so this is what we get, right? and it becomes easier because now we can now pull out the 2 times 2, which is 4, and then we have cos squared integrated, and cos squared is the same as cos 2x plus 1 over 2. And now we can now divide the 2, or we can pull the half out, so we have 2 times the integral of cos 2x plus 1. And that integrated, we have half hyperbolic sine x plus x. And we have the limits shown here properly. And then now we substitute in our limits. So we have half sinh 2 hyperbolic arc hyperbolic sine of 1 minus sinh of 0 for this, and then plus sinh hyperbolic arc sinh of 1 minus 0. So obviously this and that go away. And so this is, forget this. So we have now 2 times half. This is supposed to be 2, and this is 1. Let's so that now expanded, we have let's just erase this. Okay. So we have things in the clear here. So expanding these 2, we have 2 sinh of arc sinh of 1 cos times arc sinh of 1 plus, since this goes to 0, which is this e to the power 0 minus e to the power negative 0, which is the same as 1 minus 1. So this goes to 0. And then here we have arc sinh of 1. So this goes to 1 definitely, because it's the same. It's the sinh of arc sinh of 1. So this goes to 1. Sorry, it goes to 1. I apologize. And then this and this cancel to 1. So now we are left with 1 here, and then 1 here. So we are left with now cos of arc hyperbolic sine of 1, and then cos is the same as square root of 1 plus sinh squared. Then plugging this in here. So that means that now we are left with 1 here, 1 squared. So it's 1 plus 1, and that is root 2. Now, what is arc sinh of 1? So if y is equals to arc sinh of 1, right, means that y is equals to 1, and that means that e to the power x, y, sorry, minus e to the power negative 1 all over 2 is equals to 1. And so that means that e to the power y minus e equals 2. Right? So multiply across by e to the power y. So we have e to the power y squared minus 1 is equals to 2 times e to the power y. And so e to the power 2y minus e to the power y, sorry, 2 minus 1 is equals to 0. Okay, and we can erase this just so that we can get things on a clear footing. Let's erase this. 0/10. We have e to the power 2y minus e to the power y. This is 2 squared minus 1 is equals to 0. And so using the quadratic formula, e to the power y is equals to negative b, which is 2 plus that square root of b squared, which is 4 minus 4 times 1 times negative 1, which is another 4 plus divided by 2. So which is equals to 2 plus, this is 8. 8 is 2 times 4, so square root of 4 is 2. So we have 2 root 2 divided by 2. And this divided by this means that our e to the power y is equals to 1 plus minus, so let's say we forgot that, minus root 2. Now, the minus means that this value is negative, right? But it's not possible for e to the power y to be negative unless there is this y is an imaginary component. So y, e to the power y, therefore, has only one candidate that defeats that, and that is 1 plus root 2, and therefore 1 is equals to natural logarithm of 1 plus root 2. So arc-hyperbolic sine of 1 is the same as natural logarithm of 1 plus root 2. And so we plug that in, and that is the green integral, right? So the integral from y equals to 0 to 2 of y squared plus 4 is equals to twice the square root of 2 plus the natural logarithm of root 2 plus 1. But our original integral is negative 1 is equals to negative 1 plus the half of that green integral. So when we plug things in, we have negative 1 plus half times twice, so root 2 plus natural logarithm of 2 plus 1. So this 2 cancels. And so we are left with root 2 minus 1 plus a natural logarithm of 2 plus 1. And this is our final answer. So this has been a little bit windy, but we've shown 2 methods. I think the second method was an easier one if you really knew your way around hyperbolic sine and cosine. The first one was a little bit longer. So whatever really is something that you'd be comfortable with, you can go with it and so get back to the same answer. So it's been an absolute pleasure solving this problem. I really enjoyed it. I hope you also enjoy it. If you have a question or a comment, feel free to leave it in the comment section. Until next time, bye-bye. And there's a third method by which this can be solved. And this method was brought to our attention by a subscriber, which is first of all, obviously equating u to our integrand, 1 plus whatever is under the integration sign. And as we know, that upper part here is also equal to u, and this lower part also is equal to u, so that we have the expression u plus u equals to 1 plus u over x plus u. Multiplying both sides by x plus u, we have ux plus u squared equals to 1 plus u. And so making x the subject would first of all entail subtracting u squared from both sides. So we have x equals to 1 plus u minus u squared. Divide across by u, we get that x equals to 1 over u plus 1 minus u. Now that means that dx du is equals to negative 1 minus u squared minus 1. And so we can substitute dx with negative 1 over u squared minus 1 du. Now, since ux plus u squared is equals to 1 plus u, when x equals to 1, that means that u plus u squared equals to 1 plus u, and therefore u squared minus 1 is equals to 0 by subtracting both sides by u, and that means that u minus 1 times u plus 1 equals to 0, therefore u equals to 1 or negative 1. And since we saw from our expression that u must be positive, it means that u equals to 1. When x equals to 3, means that 3u plus u squared is equals to 1 plus u, and therefore u squared plus 2u minus 1 equals to 0. Using the quadratic formula, u equals negative 2 plus minus square root of 4 plus 4 over 2. And therefore u equals to negative 1 plus or minus square root of 2. And again, we know that within the interval of integration, u must be positive, so u equals to square root of 2 minus 1. And so our integral is therefore the same as, in place of 1, we have 1. In place of 3, we have square root of 2 minus 1. In place of the integrand, we have u. In place of dx, we have negative 1 over u squared minus 1 du. And you can pull out the negatives and then flip this limits so that we have the integral from root 2 minus 1 over to u equals to 1 of u times 1 over u squared plus 1. And so multiplying u across means that we have the integral of 1 over u plus u. And the integration of 1 over u is a natural logarithm of u. The integration of u is u squared over 2. And then we apply the limits. So log u, applying the limits, we have log 1 minus log of square root of 2 minus 1. And then here we have 1 over 2, 1 squared over 2 minus root 2 minus 1 squared over 2. And so using the rules of logarithms, we have here natural logarithm of 1 over root 2 minus 1, plus combining these two, since we have a common denominator here, we have 1 minus root 2 minus 1 squared over 2. And so multiplying both the denominator and numerator with square root of 2 plus 1, we have log of square root of 2 plus 1 over square root of 2 minus 1 times square root of 2 plus 1. And then here when we multiply or we expand this expression, we have 1 minus 2 root 2 plus 1. This plus this is 3. So we have here, first of all, root 2 plus 1 under the log function, and then 2 squared minus 1. So because this is the multiplication of the difference and the sum, so this is 2 minus 1, which is 1. So we have natural logarithm of root 2 plus 1. And then here 1 minus 3 is negative 2. Negative, negative, we have positive. So we have 2 root 2. And this 2 and 2, 2 and 2 cancel. So eventually we have, since 2 minus 1 is 1, we have natural logarithm of square root of 2 plus 1 minus 1 plus root 2. And this here, my friends, is the answer that was provided. This is a much simpler method, obviously. We really thank our wonderful subscriber. We may not have been able to do it without that suggestion. But all the same, we are very thankful to our subscriber for bringing that to our attention. The subscriber is at Apple, Alvin9167. Definitely at Apple, Alvin9167. Many thanks. And this obviously is the kind of interaction that we do encourage. So until next time, bye-bye. Keep your suggestions coming, and we promise to feature them. Bye-bye.
So problem 13 is the definite integral from x equals to 0 to x equals to 1 of 2x times 1 minus x squared over 1 plus x squared.
The problem here, as I said, is interesting. The first thing I would do is pulling out this constant out here so that we have 2 times the integral from x equals 0 to 1 of x times 1 minus 2x plus x squared, right? So we've gone ahead and expanded this part of the integrand. Now I can bunch 1 plus x squared and then separate the 2x out there. So we have x, this part of x plus times 1 plus x squared over 1 plus x squared, and definitely this and that would cancel. And then we're left with x times this 2x, so we have minus 2x squared over 1 over x squared. So we have here now x minus 2, this x divided by 1 plus x. We just do this, 1 plus x, 1 plus x squared here, multiplied by 1. We have x squared plus 1. Subtracted, we have negative 1. So this 1 here is what we have here. And then this negative 1 here is what we have here. And so you can go ahead and just pull this minus 1 over x squared. So we have x plus 2 over 1 plus x squared minus 2 as the integrand. And so we have 2 here outside, and when we integrate x, we have x squared over 2. When we integrate this is anything 1 over 1 plus x squared when integrated is arctangent of x. So we have 2 times arctangent of x minus 2 integrated is 2x. So the limits 0 and 1 can be applied. 0 across all this cancels to 0. And so when you substitute 1 here on the upper side of these limits, we have 1 over 2, 1 squared over 2, plus 2 arctangent of 1 minus 2 times 1, which is 2. And so half, we have now 2 times a half plus 2 arctangent of 1 minus 2. This half minus 2 is negative 3 over 2. And arctangent of 1 is pi over 4. So we have here 2 times pi over 4 minus 3 over 2. This and that goes to 2. And then when we multiply 2 across, we have pi here. And then 2 times 3 over 2 is minus 3. And this is the answer that was provided. As I say, this is a very simple problem. I hope you also do get to enjoy solving it. Thank you. Till next time, bye-bye.
Problem 14 is the indefinite integral of e to the power x plus 3x.
I can try to rearrange this problem a little bit. And how I do that is using the rules of exponents. When you do have addition in the powers, it means that, and having the same base, it means that that's the same as the multiplication of the base to the power of 1 and the same base to the power of the other part that is being added. So here, e to the power x plus 3x is the same as e to the power x times e to the power 3x. And then e to the power 3x is the same as e to the power x to the power 3. We could distribute e to the power 3x a little bit in a different way. So it's the same as e to the power x to the power 2 times e to the power x. And if we let u to be equal to e to the power x, that means that du dx is the same as e to the power x. And so you could substitute e to the power x times dx with du. And so for our problem here, it means that this part here is u, this part here is u, and this part here is du, right? And that's what we've done here. So same as e to the power u, u squared du. And then obviously the derivative of e to the power u is the same as e to the power u. So this e to the power is the same as the derivative of e to the power u with respect to u. And so using integration by parts, where if you have capital U dv, that's the same as uv capital U capital V minus the integral of capital V du. Right? And so here, because we could take v to be e to the power u and u to the power and u to be u squared. So uv is the same as u squared times e to the power u minus the derivative du is 2u. So constant 2 comes out, and then we have u to the power u times e to the power u. And then we can repeat the same process here, e to the power u being dv. I mean, the derivative of u being the derivative of e to the power u being equal to dv. So v is the same as the power u, and u being equal to u. So uv being equal to u to the power times e to the power u minus, it's here, derivative of v, which is going to e to the power u, times derivative of u, which is just 1. And so eventually we can now combine this up. So we have u squared times e to the power u minus 2u e to the power u minus minus becomes plus. The integral of e to the power u is the same as e to the power u plus the integration constant c. And so if we have that expression, since u is equal to the power x, where u appears, we can plug in e to the power x. So our original integral of e to the power x plus 3x is the same as e to the power x squared times e to the power x because of this u minus 2 times the power x times e to the power x plus 2 times e to the power x plus the integration constant. Can rearrange things a little bit. This e to the power x squared is the same as e to the power 2x times e to the power x minus 2 the power x times e to the power x plus 2 times e to the power x. Pulling e to the power x out, so we have e to the power 2x minus 2 e to the power x plus c, all multiplied by e to the power e to the power x plus the integration constant is what we get. And that's the final answer. So yeah, thank you so much for following along. I hope you did enjoy solving this. There are probably other ways of solving this, like using logs. But other than that, I think this is an interesting problem. And so till next time, Atutulu halat question for.
So problem 15, which is the definite integral from x equals to negative square root of 3 over 2 to positive square root of 3 over 2 of 2 times into bracket 1 minus the absolute value of x over square root of 3.
I would really encourage you to consider subscribing to the channel. So the first way is to plot a graph of the integrand. And so if we have y and x, the absolute value of x over root 3 is going to be like this. So the positive value, you have this line that has a gradient of 1 over root 3. Negative side, instead of the y equals to x over root 3, which would be a negative, it's positive because we're getting the absolute values of the x's. So in other words, it's a mirror image of whatever is on the positive side along the y, the x equals to 0 plane or the y-axis. Now, therefore, 1 minus x, absolute x over 3 is going to be like this. So at 0, where the graph x absolute x over root 3 is 0, 1 minus that is equals to 1. And when this graph is 1 is when this entire graph crosses 0 and continues like that all the way in the negative direction. So therefore, these graphs cross each other at root 3 over 2, negative and positive, right? So that the area under the graph between this root 3 negative over 2 and root 3 over 2 positive is going to be equal to this rectangle, the area of this rectangle, and then plus the area of this triangle, right? Times, since we have this constant 2 that has come out, times 2. So this is essentially what is going to happen. Now, the area of the rectangle, the length is twice root 3 over 2, which is root 3 here, length. And the height, midway, is a half times a half. And then for the triangle, a half base height, which is a half is a half, and then the base is still root 3. The height is going to be a half. As you can see, these 2 and these 2 cancel. These 2 and these 2 cancel. So we're going to be left with root 3 plus root 3 over 2, which is 3 root 3 over 2. And this is the answer that was expected. Very easy, no nebulous calculus involved, just area of the shapes. Method 2, we could split this integral into two subcomponents, the negative side and the negative side, because you're looking at the absolute, so it becomes a negative of the x, and the positive side will just remain with the x. So we have negative root 3 over 2 to 0 and 0 to root 3 over 2. And so this becomes positive. Negative, negative is a positive, and then this remains as it is. And if we say that let x be equal to negative x prime, such that dx is equals to negative dx, right? And the limits, negative becomes a positive, and so this becomes negative dx prime, and then this becomes negative dx, and this becomes positive. We get integral negative, because this negative here now comes here, 2 times the integral from x equals to root 3 over 2 to 0 of 1 minus, this minus here is here, x over root 3 and dx. Now, this sign can be removed by flipping the limits. So we have 2 times the integral from 0 to root 3 over 2 of 1 over x over root 3, and the same thing happens here. So eventually we just do have twice that, which is 4 times the integral from x equals to 0 to root 3 over 2 of 1 minus x over root 3. And then these are easily integratable variables. So 1 becomes x over root 3 is x squared over 2 root 3, with the limits root 3 over 2. So 4 root 3 over 2 in place of this x here. And then root 3 over 2 squared, root 3 over 2 squared over 2 over root 3. And as you can see, one of the root 3 in the square here cancels, and so we left 1 root 3 here, and then this 2 square is 4. 4 times 2 is 8. So we have 4 outside here, root 3 over 2 minus root 3 over 8. And when you multiply across with the first here, we have 2, 2. So we have 2 root 3. 4 and 2, so we have a half, so root 3 over 2. So 2 root 3 minus root 3 over 2. And so this is same as 4 root 3 minus root 3 all over 2, so which is root 3 over 3 root 3 over 2. And this is also a final answer. So very interesting solutions. One involved just plotting it out, and that was a simpler method. But the next one involved really grinding through the calculus, which is not really hard, but it needed extra interpretation of things. So until next time, I would really appreciate your continued support. Stay tuned and take care. Bye-bye.
So problem 16 is the indefinite integral of natural logarithm of 1 plus x squared over x squared.
This problem here, I think the best strategy is using integration by parts. So looking at the denominator of the integrand there, x squared can be expressed as the derivative of the negative 1 over x. And so using integration by parts, which basically tells us that if you do have a integral of a product of capital V and capital du, capital D capital U is equals to, the answer is the product of capital U and V minus the integral of capital U dV, and that's capital V. So here our V is natural logarithm of 1 plus x squared, and our u, capital U, is negative 1 over x. So in other words, our uv is going to be negative natural logarithm 1 plus x squared over x, and so minus the product of 1 over x, and that minus and this minus here form the positive sign here, and then the derivative dv of natural logarithm of 1 plus x squared is 2x over 1 plus x squared. So this x and this x cancels, and so we have negative natural logarithm 1 plus x squared over x plus 2 over 1 plus x squared. And we can pull that constant 2 out, and so we have negative natural logarithm 1 plus x squared over x plus 2, the integral of 1 plus 1 over 1 plus x squared, right? And the integral 1 over 1 plus x squared is a popular integral that amounts or results into the arctangent of x. And then obviously we have the integration constant here. So this is our answer, negative log, natural logarithm 1 plus x squared over x plus twice the arctangent of x plus the integration constant. This is the answer. It was simple, straightforward, but all the same interesting. So for those of you who haven't subscribed to our channel, we do really encourage you to subscribe to our channel. Please, if you like what you see, please click on that like button and keep it locked. Until next time, bye-bye.
Problem 17 is the indefinite integral of 2 to the power x times x squared.
So for this problem, the first thing one would do is choose one of these. I choose 2 to the power x. And I say let u be equal to 2 to the power x such that natural logarithm u equals to natural logarithm of 2 to the power x, and using the laws of logarithms, the x goes this side, such that 1 over u du dx is equals to natural log of 2. And so du over u log 2 can be substituted for dx. Now the integral 2 to the power x times x squared can now be expressed as, in place of 2 to the power x, we have u, in place of x squared. So if you look at this here, x is the same as log, natural log u over log 2. And so x squared is natural log u over natural log 2 all squared. And then in place of dx, we've now brought this du over u times natural log 2. And so we can pull out the natural log 2 out. So we have 1 over log natural log 2 squared times log 2. So in the as a constant here, we have 1 over natural log 2 to the power 3. And then this u here and this u cancel each other. And now we're left with natural log u squared. Some people would like to express that as log squared. I prefer to just keep it in brackets the way it is right now. And so this expression here can also be written as, because there's a hidden 1 here, times 1, which can be expressed as the derivative of u. And so using integration by parts, where if you have a product of u, capital U, and a product of d, capital V, when integrated, that is the same as u, capital U, times capital V, minus the integral of capital V times d, capital U. Now, u here for us is log u squared, and dv is the derivative of u here. So that now our answer here would be the product of u and v first, which is going to be log u squared times u. And yeah, minus v du is going to be, since our v is u times, if you have your function y equals to log u squared dy du is equals to 2 times log u times the derivative of log u. Right? Now the derivative of log u is the same as 1 over u. So we have 2 log u times 1 over u. And this is exactly what our d capital U is. Put it here, right? Now, as we can see, this u and this u would cancel each other. And so we are left with 1 over natural log 2 cube brackets u times natural log u squared minus 2 integral log u. We'll repeat the same process where we say, okay, there is a minus times 1 there. There's a hidden times 1 there. And so we have natural log u times the derivative of u, which is the same as 1. And so using the same process of integration by parts, we have a nested bracket that we're going to develop. So we have minus 2 here in bracket u log u minus bracket is v, which is u times the derivative of log, which is 1 over u. So that would cancel. And so we have 1 over natural log 2 cube in bracket u times natural log u squared minus 2 u times log u minus the derivative of, the integral of 1 here. And integrating 1 means that we just have a variable u as a result, right? And then the integration constant as usual. So we've gone back to the best of things, but there's one thing that we had done initially, and that is to substitute for 2 to the power x with u. And so we're going to have to bring back the 2 to the power x to complete our integration. So the integral of 2 to the power x times x to the power 2 is 1 over log 2 to the power 3. In place of u, we have 2 to the power x. In place of log u squared, we have log 2 to the power x squared minus, in place of u here, log 2 to the power x. In place of log u, log 2 to the power x minus, in place of u to the power x. You can open up those brackets and also shift things here where we have exponents. We can pull back that, and then add the same thing here, right? And then pull out 2 to the power x eventually. But as you can see, this x goes here, and then because we have squared here, it becomes x squared. And then here we have x going down. And then when we open the brackets and factor out the 2 to the power x, we have x squared times log 2 to the power 2 times 2x log 2 plus 2, and then plus integration constant. And this is the answer we've been looking for. So thank you so much for tuning in. We appreciate your support. Until next time, we can say bye-bye.
So problem 18 is the definite integral from x equals to 0 to x equals to 1 of the square root of x to the power 8 minus x to the power 6 plus x to the power 4, that multiplied by the square root of 1 plus x squared.
Problem is interesting. My simpler version of the solution is first, I would like to combine those square root signs so that we have one big square root sign. So I would just multiply x to the power 8 minus x to the power 6 plus x to the power 4 and 1 plus x squared under the square root sign. So what happens here is essentially this part here times 1. So we have this. And then the same part here times this, right? So x to the power 8 times x squared is x to the power 10. X to the power 6 or minus x to the power 6 times x squared is minus x to the power 8. And plus x to the power 4 times x to the power 2 is x to the power 6. Now what we see here is this one here and this cancel, and this cancel, right? So we are left essentially with these two components. So, and that is x to the power 4 plus x to the power 10, all under the square root sign. Then we can pull x to the power 4 out, and when you get the square root of that, we have x squared, and then 1 plus x to the power 6, which is interesting. And the next step for us is to say, okay, let's combine this x squared and dx. And we see that if we let u be equal to x to the power 3, that means that du dx is 3x squared. And so a third du can be substituted for x squared times dx. So this here is the same as this, right? And so we can substitute that for that block. Now, when x equals to 0, for the lower limit, u is equals to 0 to the power 3, which is 0. When x equals to 1, u is equals to 1 cube, which is 1. Right? So this limit here can be substituted appropriately. And so for our new integral, in place of du, in place of dx, x squared dx, we have a third du. So we pulled out a third. In place of x equals to 0, we put u equals to 0. In place of x equals to 1, we put u equals to 1. And in place of 1 plus x to the power 6, we have 1 plus u squared, because x to the power 6 is the same as x cubed squared. And so we can then go ahead and say again, let u be equal to tan theta, such that du d theta equals to sec squared theta. And so du can be substituted for, or sec squared theta, d theta can be substituted for du. Now, let me also just do one more diligence. Since u is tan theta, when u equals to 0, that means theta is equals to arctangent. Just my preference to represent arctangent like that, which is equals to 0. When u is equals to 1, sorry, now when u equals to 1, theta is equals to arctangent of 1, which is equals to pi over 4. So the limits, the lower limit is 0, the upper limit is going to be pi over 4 in the theta domain. Therefore, a third integral from u equals to 0 to u equals to 1 of square root of 1 plus u squared du is the same as a third. Lower limit is 0, upper limit pi over 4, square root in place of u squared, we have tan squared theta. In place of du, we have sec squared theta. And so 1 plus tan squared theta is the same as sec squared theta. We have a square root sign here, obviously. And then we have sec squared theta d theta that we substitute in place of du. So we have a third integral from theta equals to 0 to theta equals to pi over 4. Square root of sec squared theta is sec theta times sec squared theta. Now, sec squared theta can be expressed as the derivative of tangent of theta. And we can now use the integration by parts, where if we have a product of u capital U, d capital V, the integral of that is u capital U capital V minus the integral of capital V product d capital U. And so if our u is sec theta and our v is tan theta, uv is going to be equal to, we pull obviously this constant out here, sec theta tan theta, and we've applied the limits shown here, minus the integral of from obvious theta equals to 0 to theta equals to pi over 4 of v, which we found to be tan theta, and then derivative of du or sec theta, which is sec theta d theta. So we have sec theta tan square theta. Continuing, we can now express tan square theta in terms of sec theta. So tan square theta is the same as sec square theta minus 1. And so we are left with sec cube here and sec theta here. So since this entire integral is a third integral of sec cube theta, then we do have an I here. So we have a third integral of sec theta, obviously with the limits, sec cube theta with the limits. And then in that, we still have sec cube theta. So we decide to, on the left side, say, okay, we have a third, the integral I. But again, here we have another I here. Now, there's this constant here, I mean 1 over 3. So 1 over 3 times I can be pulled onto the left-hand side, and we have 2 over 3 I. And we're still left with this part and this part, okay? But our integral of interest still has to be a third I. So we have to divide both sides by 2 so that our third I is 1 over 6. This part here, which has already been integrated with the limits as shown there, times the integral of sec theta from theta equals to 0 to theta equals to pi over 4. Now we can just apply the limits, sec pi over 4 tan pi over 4 minus sec 0 tan 0. Sec tan 0 is 0, so 0 times sec 0, which is 1, this entire thing goes to 0, okay? Now, sec pi over 4 is square root of 2. Tan pi over 4 is 1, so this is going to be root 2. Now, this integral, I can solve it easier or easily if I apply this constant here that is 1, but we express as 1 plus sine theta over 1 plus sine theta, right? So that means that we have 1 plus sine theta over cosine theta times 1 plus sine theta. This 1 here can be expressed in form of the identity cosine theta, sine square theta plus sine square theta. Okay. This one here is the same as 1. And that will help us quite a bit because then it means that we can separate it into two different additions, integrals, sorry, and we can factor out the second part where we pull sine theta out, and as you can see, these two different integrals. In this case here, this and this one cancels, and this and this cancels. Right? And then that means is that we have now cosine theta over 1 plus sine theta here, sine theta plus cosine theta. We can combine that integral again, and so we have cosine theta over 1 plus sine theta plus sine theta over cosine theta. Now, this integrated is the same as the natural logarithm because the numerator is the same as the derivative of the denominator, and then here the denominator, the numerator is the same as the negative derivative of the denominator. So we have natural logarithm 1 plus sine theta minus natural logarithm of cosine theta. Applying in the limits appropriately, we have, first of all, I had to use the rules of logs where we're dividing when there's a subtraction of the two different logs. So we have to combine it to one log function and then divide whatever is under the log function. So we have the log function. So we have sec theta plus tan theta. And applying in the limits, we have obviously our root 2 there, and then natural log of sec pi over 4 plus tan pi over 4 minus natural log of sec 0 plus tan 0. So this one here is 0, this here is 1, and this one here is 1, and here is root 2. Okay. And therefore we have a constant 1 over 6 root 2 plus natural log root 2 plus 1 minus log of natural log of 1 plus 0, which is just natural log of 1. So any log of 1 to any base is 0. So we're left with 6 root 2 plus natural log of root 2 plus 1. And that's our final answer. So Kind of windy, but all the same interesting. Until next time, bye-bye. If you haven't subscribed to our channel, we do invite you to subscribe to our channel. We would really appreciate your support. If you have a question you'd like us to get back to you, please leave a comment in the comment section. If you have any suggestions or alternative methods, we would really appreciate it. We'd love to learn from you. Thank you. Until next time.
So problem 19 is the definite integral from x equals 1 to x tending to infinity of e to the power x plus x times e to the power x all over x squared times e to the power 2x minus 1.
So the first thing that I usually would be kind of interested in is I look at the denominator here and I see a square. And that means that I could use the difference of two squares and the sum of two squares idea. When you multiply them, then you do have an expression like this, since 1 is 1 squared. So I've decided to bunch these together. So we have x times e to the power x here, the denominator, square. And since we know that a squared minus b squared is equals to, in brackets, a minus b close bracket times a plus b, right? So this difference of two squares, a squared is this term here, and b squared is 1 squared here. So we can now express this as e to the power x plus x times e to the power x over x times e to the power x plus 1, the sum part here, yeah, and times x times e to the power x minus 1, and that is this, right? Now, we can now go ahead and express this as a partial fraction. Now we do that ignoring the numerator. The denominator, 1 over the denominator is the same as 1 over x times e to the power x minus 1 minus 1 over x times e to the power x plus 1 times a half. Because when you combine this, you have a 2 in the numerator, and to cancel that 2, we have a half here. Then now, multiplying this numerator across, we have half times the integral from x equals to 1 to x tending to infinity of e to the power x plus x to the plus x times e to the power x over x times e to the power x minus 1 minus x e to the power x plus x times e to the power x over x times e to the power x plus 1. Now, when I look at these here, this is the same as the derivative of, right? X times e to the power x, right? That's the same thing, because when you use the derivative of a product, pass away, differentiate x and multiply by ex, so the x goes away, you have x here, and then x times the derivative of e to the power x, the derivative of e to the power x is the same as e to the power x, so this is what we have. But as we look at the denominator, we see that there's a difference here. There's a minus 1, and this is a constant. So this is the same as the derivative of x e to the power x minus 1. Same thing. And the same thing on this side, this is the same as the derivative of x times e to the power x plus 1. And so we can go ahead and say, okay, here, the numerator is the derivative of the denominator. The same thing here, the numerator is the derivative of the denominator. So that means that when we integrate it, this is the same as the natural logarithm, half times the natural logarithm of x times e to the power x minus 1 minus the natural logarithm of x times e to the power x plus 1, right? So the next thing is using the rules of logarithms. When you have the difference of two log functions, that's the same as the log function of the quotient of whatever is under the log functions, okay? And so we have x times e to the power x minus 1 over x times e to the power x plus 1. Now, because I have an infinity here, I like to express it inside this expression in such a way that when I get a limit as x tends to infinity, I have something that is finite. So what I do is I divide both sides by x to the power ex so that I have 1 minus x to the power negative x over 1 plus e to the power negative x over x, all that under the log function, such that when x tends to infinity on the upper side, the numerator here tends to 0, and then 0 times 0 because 1 over x also tends to 0. And so what we get here is that on the upper limit as x tends to infinity, this part here tends to 1 over 1 minus limit as x tends to 1, we have 1 minus e to the power negative 1 over 1 plus 1 over 1 plus e to the power negative 1 over 1. And so log 1 minus 0, 1 plus 0, minus log 1 minus e to the power negative 1 over 1 plus e to the power negative 1. So the e to the power negative 1 is the same as 1 over e, multiply across by e, and we get, since log 1 here from here is 0, so that goes away. And here we have minus log e minus 1 over e plus 1. The negative here can go up here as power negative 1, right? And that means that we get the reciprocal of whatever is under the log function. And so we have half natural log of e plus 1 over e minus 1. And that is the answer. Thank you so much for tuning in. We do appreciate your support. Means a lot. If you haven't subscribed, please press the subscribe button. We'll love your support. Share, comment. Your support would mean a lot. Thank you. Until next time, be blessed.
Problem 20 is the definite integral from x equals to 0 to x tending to infinity of, in bracket, 80x cubed minus 60x to the power 4 plus 14x to the power 5 minus x to the power 6 close bracket times e to the power negative x.
So this problem is obviously, it looks ugly, but the thing that one could look at is there's so many x to the power 3, 4, 5, we could try and see a general approach to this. So if we have x to the power n times to the power negative x, that can be expressed as the e to the power negative x can be expressed as the derivative of negative e to the power x. And using integration by parts, where if we have capital V d capital U being equal to capital U capital V minus the integral of capital U d capital V, where V now is our negative x, and then U here is negative e to the power x, and V is x to the power n. Therefore, our U, the product of U, capital U and capital V, is negative e to the power negative x times x to the power n. And obviously applying the limits appropriately, minus, and then since we have this negative here, coming plus n x to the power n minus 1, which is the derivative of x to the power n times e to the power negative x. So applying the limits here as the limit of x tending to infinity of this, since this tends to 0, the entire thing tends to 0. And here, as x tends to 0, since this tends to 0, this entire thing tends to 0. So this reduces the integral down to n times the integral of x to the power n minus 1 times e to the power negative x from x equals to 0 to x tending to infinity. We can repeat that same process and realize we can keep doing it, and it continues in that fashion. The constant reduces all the way up to 1, at which x to the power 0 is what we get, and so this becomes 1, and so we have the integral of n factorial times, we have n factorial times the integral of e to the power negative x from x to 0 to infinity, or x and infinity. So when we integrate e to the power negative x from 0 to x tending to infinity, that becomes 1. And so our answer, because this tends to 0, right? And this tends to 1. X to the power, e to the power negative 0 is 1, minus minus plus. So we have n, the product of n times n and n minus 1, n minus 2, all the way up to 1. So n factorial. So what this tells us is that the integral from x equals to 0 to x tending to infinity, right? Of x to the power n times that is n factorial. And so what that means that when we have this problem here, and you multiply e to the power negative x across, this is 80 times 3 factorial, 60 times 4 factorial, 14 times 5 factorial, and this is 6 factorial. So 80 times 3 factorial minus 60 minus 4 factorial plus 14 times 5 factorial minus 6 factorial. 3 factorial is 6, 4 factorial is 24, 5 factorial is 120. And so 80 times 6 is 480. 60 times 24 is 1,440. 14 times 120 is 1,680. And then 6 factorial is 720. And so when you do this arithmetic, it all comes down to 0. And that is the solution to our problem. So it's a very easy problem, but it just did require one to have that general inkling. If you try to solve everything independently, yes, you might get to the answer, but obviously it comes at an extra overhead. So thank you so much for tuning in. This is the last problem of the MIT 2024 integration regular season. We hope you did enjoy following along. If you do want to see how the other problems were solved, please look at our channel. We do have all these solutions laid out. We do welcome your questions and your suggestions and your thoughts. We're here to learn. Thank you until next time. Bye-bye.